we started discussing with you why we need eigenvalues and eigenvectors. The first and the major reason for that is this something which I call diagonalization. This is a slide we discussed with you last week, which explains briefly what diagonalization is. I'll take you through the slide and then I'll show you a few examples. And that today we'll have like a lecture a bit shorter than regular because our school is planning to come and help you to do cat-eye. You know, the cat-eye, that's where you give your feedback on the course. Given that normally students are a little bit passive on this in this activity, they want to encourage you to do it here in class because you can do it on your phone. I hope you understand the reason for that. We value your feedback. It may sound like a cliche, but we do. We make adjustments for the depending on the feedback. So your feedback is something we need, and that's why there will be another academic from the school a bit later today who will come and just guide you through the process on your phones. There will be also a cat-eye for my teaching evaluation. That's where you can tell you what you think about my teaching. It's another feedback which I personally value. That's something for me. If you want to help me or if you want to like snap at me, that's the time to do it. And again, whatever you have to say, I encourage you to say that because the more you say, the more it will influence my further evolution. So please just don't take it as a banality. Just be a little bit more active than a regular student and do your contribution towards improving what we have here. Anyway, so diagonalization was about this. If you have a matrix, it's always about square matrix. So if you have a square matrix, here it is. If you know spectral components involved for such a matrix, and that's what I mean by that. If you know all of the eigenvalues or some of the eigenvalues, and you know some of the eigenvectors associated with that, you can build two matrices based on this knowledge. You can build a P matrix, which consists of your x vectors as columns, and you can build your D matrix, which is a diagonal matrix with entries on the diagonal, just eigenvalues. That's right. These two together, they linked to your A matrix through this relation. If you do the multiplication of this type, AP, that will be the same as PD. That's something which I call semi-diagonalization of A, this relation, exactly this relation I call semi-diagonalization. The reason why this is true is in these two lines. We looked through these two lines in quite detail last week. Now, on the top of this, if you have enough eigenvalues and eigenvectors, and by saying enough, I mean if you have n of them, if this m, you see m is a number of eigenvalue, eigenvector pairs. If you have enough of these pairs, I mean as much as the size of your matrix, and on the top of that, the vectors are linearly independent. That's what I mean by enough. Then your P matrix becomes square matrix because you will have as many columns as rows, and not only that, because it's linear independent, it will be invertible matrix, and you can convert this relation, this semi-diagonalization relation, into a full or complete diagonalization relation, which is like this, or like this. These two are equivalent, and this is what we call diagonalization. Okay? That's the first application of eigenvalues and eigenvectors. There will be a few others which grow from here, from diagonalization. Diagonalization in many applications, in most of the applications, it's at the base of everything. When you have diagonalization, you can move on from that into other areas. I'll show you a few examples how this works now, on numerical examples, to save us time. I will use those. I mean, we've done quite a few examples already where we found all of this spectral information for a few matrices before. It was either like by guessing or by characteristic polynomial or through a few shortcuts for 2 times 2 matrices. We had a few examples where we found all of the eigenvalues available, all of the eigenvectors available. So to save us time, I will take those examples from last lecture, or from lecture 2 lectures ago, from 3 lectures ago. That's where we are. 2 or 3 lectures ago, we started discussing your eigenvalues and eigenvectors. I will take those examples and I will take them further to the diagonalization stage. That will save us time because we don't need to recompute the eigenvalues. We don't need to recompute this bit from where the diagonalization starts, okay? So first I'll take the 2 by 2 matrix example. That's the example that's why actually before we do that, actually one extra thing from Thursday last week. So this is a diagonalization. Another thing which we discussed with you at length, as a matter of fact, on Thursday is that how to achieve this extra bit on top of this one, because this one we know how to do. It's basically it's a routine thing. It may be lengthy. It may require a number of steps, and you need to be disciplined. You need to exercise quite some discipline to make sure your computations are correct. But these are the routine ones. And that will give you the semi-diagonalization. To get this extra bit, to get this linear independent vectors, in order to get complete or full diagonalization, it's a harder business. And on Thursday, I gave you one of the results, which the easiest result there is, which will ensure this extra one. It's something which I call, I'll show you this slide now. It's something which I call this result. Look at this result. That's a result we discussed at length on Thursday. This lemma, which says in case you have pairwise distinct eigenvalues, you can always expect that the associated eigenvectors are linearly independent. It's a good result. It's about one of the easiest ones in this business. And there will be a few opportunities today where I will reference this result. Okay. Now we go to the examples. The first example. Diagonalization one, it's the one which this part which we need to do diagonalization. We computed with you 2 lectures ago. I'll show you this on the website. It was here, lecture, yeah? Yeah, no, it's not here. It's lecture 19, this one. It's the one which I call efficiency tricks when you find e-values or e-vectors in 2 times 2 matrices. So we did one example there. That's a slide. The efficiency trick was that when you go for the eigenvalues or eigenvectors of a matrix which is 2 times 2, you can do guessing. On many occasions you can do guessing. And that's here I explain guessing, but I'm going to take this example from this slide. Example, tutorial question 7 part C. Here's a matrix. For this matrix, on lecture 19, we found 2 eigenvalues. Here they are -6, 3. And we found 2 eigenvectors. One of them is -5, 9. And the other one, 1, 0. This is the thing I'm going to take from this slide now, and I'll take it now further to diagonalization on my new slide. So keep in mind. So I'm taking this example we've done on lecture 19, 2 lectures ago, right? Today is lecture 21, isn't it? Yes. And now we go to my dynamic slides, and we just go to the example. Here's the information from that lecture. So it's my first slide, diagonalization example 1. Here's a matrix from that slide of lecture 19. 2 values we found on that slide, a -6 and 3, and 2 vectors associated with that, 1 and 2. Even at this stage, I can already comment on the linear independence of my eigenvectors. Well, in this case, of course, probably you can see it even directly that these 2 vectors are linearly independent, because otherwise they wouldn't be one would be scalar multiple of the other. But this observation is in line with the lemma I just showed you. 2 distinct eigenvalues possess 2 linearly independent eigenvectors. So in this case, we can expect a full diagonalization because we have enough of eigenvector pairs, and vectors are linearly independent. So in this case, we will have a full diagonalization identity. Look at this. So all I need to do, I need to build my P matrix from my eigenvectors as columns. Here they are. I need to build a D matrix from my eigenvalues on diagonal, and the rest is 0. That's right, and I can be absolutely sure of, like, from our general discussion, from our quite detailed general discussion on Thursday, I can be absolutely sure that if I compute the product AP, that's the A matrix from here, that's the P matrix, the one which we built right here. If I compute such a product, and if I compute the product PD, these two results will be the same. That's the full diagonalization. Sorry, that's a semi-diagonal. That's something which I call semi-diagonalization. These two results, they must be the same. We will do a double check. Let's just do multiplication. This multiplication is, I claim it is 33, negative 54 is 0. Let's just double check. So it's this row times this column. It's negative 15 plus 45. It's 30. Then this row by this column, it's 3. Then last row and the first column, it's negative 6 by 9, it's negative 54, no objections here. And the last row and the last column is simply 0. So this is a product AP. This is a product PD. Let's just double check. In fact, there isn't much to a double check. Remember the other efficiency which we discussed with you on Thursday? When you multiply something by a diagonal from the right-hand side, all you need to do, you need to scale the columns by the diagonal entries. So I need to scale this column by negative 6, and I need to scale this column by 3. That's the way you do multiplications when one of the factors is a diagonal matrix. It's a very effective way of doing multiplications. That's something we discussed with you at length, and that works here. Look at this. If I take this negative 6 and multiply this column by 8, it will be 30. Good. Negative 54. And then this 3, if you scale the last column by it will be 3, 0. And you see, the result is the same. Quite expectable. We expect this from our general thinking, line of thinking from Thursday, but it's a good confirmation of that. So this AP is indeed the same as PD, and that is something which I call semi-diagonalization. If I want to see full diagonalization, I need to address the issue of invertibility of my P matrix. Again here, from the general perspective, I can be absolutely sure that my matrix will be invertible because my eigenvalues are distinct. For such eigenvalues, eigenvectors are always linearly independent, and we have enough of them. We have 2 of them in the matrix of size 2. So we have a square matrix. We can invert it. Well, formula-wise, I'm sorry, I opened the wrong thing. Formula-wise, where is this? Yeah, okay. For a matrix of size 2 times 2, the inverse, we have just a direct formula. Here it is. For the inverse of the matrix of size 2 times, I'm not sure if you remember that formula. It's a good actually thing, a good practice to remember this formula. And your inverse exists if and only if this denominator value is non-zero. It's determinant of your 2 times 2 matrix, isn't it? It's AD take BC. It is exactly the determinant of it. If it's 0, then you don't have the inverse. If it is not 0, you do have the inverse. That's the formula for the inverse. If I use this formula for my P, here it is. Here's a usage of this formula for P. I claim that the determinant here is negative 9. It's true. It's 0. Take 9. It is negative 9. And then I just rearrange the entries in the way it is shown here. I just flip the entries on the diagonal. You see, AD went into GA, 0, 5, and I just negate the other entries. So this is the inverse. Or this is a simpler version of the inverse if you just take care of negatives. If you take care of negatives, and I can be absolutely sure that not only this identity holds, AP equals PD, but this identity holds as well, and that's something which I call a complete diagonalization. But we don't need to check this numerically. This is true from the general consideration, and that's all there is to it. That's how diagonalization works, at least on the level when you need to discover these 2 matrices, P and D. What you can do with it, I'll show you a few further advancements for what you can actually do with it a bit later, but for now we're just discussing how to discover these matrices and double checking this numerically that this is indeed how it's supposed to be. Yeah. Any questions? I'm sorry, yes, please.
Determinant for this one, just L1 minus X, and that minus would it be?
I'm sorry, I didn't catch it. Say again, please.
Would the determinant just be lambda 1 minus lambda 2?
Minus lambda 2, you said.
Lambda 1 minus lambda 2.
Minus?
Yeah.
Did you say minus? No, it can't be. From the efficiency tricks, the one which I just showed, the slide from where this example came from, if you remember, this one. If you're done, I need to switch the slides. I'll bring this back if you have any further questions. I'll show you what. From the efficiency one, remember this, the slide I just showed you. I showed you this on the PDF from the website. It's a dynamic version of it, but we discussed this 2 lectures ago, lecture 19. Here, the connection of the determinant to the eigenvalues here. These are the relations we discussed with you 2 lectures ago. Determinant of the matrix, if it's 2 times 2 matrix, is the product of lambda 1 and lambda 2. It's not a difference. It's not minus, it's times. If you want to sum them, again, not minus, if you plus them, that will be another invariant. It's called trace, and that is just the sum of the diagonal entries. You see A plus D. So to some extent, you're right. Eigenvalues in the proper combination, they have linkage to fundamental numbers associated with metrics. In fact, these relations, they exist also for the matrices of higher size. I didn't mention that 2 lectures ago, but as long as you raise this question, I can comment on that. These relations, they work for matrix of any size. I mean, if you have a matrix of size nn, say, like this, not specifically 2 times 2, size nn, and if you know all of the eigenvalues and all of the eigenvectors, well, they're just eigenvalues, you have a similar relations there. In that case, it will be trace of your matrix, and in case n times n, trace again will be the sum of all of the entries on the diagonal, disregarding the rest of the matrix, just the diagonal ones. The sum will be the sum of all of the eigenvalues. This time it will be more than 2. It will be n of them. And you have to, if the eigenvalue comes with the multiplicity higher than 1, you have to add this value as many times as the multiplicity is. But the similar relation will still hold. And for the determinant, it will be again a similar relation. The determinant of A will be the product of all of the eigenvalues, all of them. The reason I didn't mention, or I didn't focus so much on these relations in the size, for the matrices of size higher than 2, is just they don't help you guess values. They're still present there. They're true. You can use them, but they helpless in regarding the guessing the eigen, because when you have just two relations, you can do guessing. In a similar fashion, you do guessing for the roots of the quadratic equation. When you have size higher than 2, you no longer can do guessing. Sometimes they can help. So it's worth remembering them if you want to remember them. If you have some spare room in your head, you can remember that. But it's not as valuable as the 2-dimensional versions. But as long as you mention that, here they are. Let's just go back to that slide. We just discussed. Any other questions in relation to this example? I have another 2 examples of diagonalization. Again, to save us time and computation effort, I will take the examples we pre-computed before. This time it will be the example of 3 times 3 matrix. We've done, if I look for the history here, I'll tell you when we've done it. I believe we've done it here in lecture 18. That's the one. Example of using characteristic polynomial. We've done this example with you, lecture 18. There was an example there of 3 times 3 matrix. This one. That's the matrix. For this one, we found all of the eigenvalues and all of the eigenvectors. Look down here. There was a value 5 on lecture 18. And for that value, we had only one eigenvalue, 1, 5, 25. See, right here. And there was another value, if I remember correctly. Yeah, well, it just cut across the pages here, but it's 2 right here. And for that value, we had 2 eigenvalues. 2. One of them was 1, one of them was 1, 2, 4. Oh, wait a sec. How come? No, that's right. I'm sorry. My apologies. There was only 1 here. It's here. 1, 2, 4. Sorry. So 2 eigenvalues, 5 and 2, and 2 eigenvectors, 1, 5, 25, 1, 2, 4. Again, according in full agreement with our general result, distinct eigenvalues correspond to the linearly independent eigenvectors. This vector is linearly independent from this one. One of them is not scalar multiple of the other. So in this example, even now you can see that we won't have full diagonalization. We don't have enough eigenvalue eigenvector pairs, right? Because it's a 3 times 3 case. We need 3 pairs to have a full diagonalization. We only have 2 pairs, which means we will only have the semi-diagonalization. We just go back to my dynamic slides. I'll show you. So it's a second example. I just copied those results, those vectors from the slide of lecture 18. That's the matrix we had there. One value, sorry, that's the other value. And the vectors from that slide, here they are. 2 vectors, 2 eigenvalues, linearly independent because we have a distinct eigenvalues. You can write up semi-diagonalization relation. So you can say, we can build up the P matrix, which consists of my eigenvectors as columns. One column, the other column. I'm fine with this. You can write up the D matrix, even though this time diagonal, it's a bit loose term because it's not, sorry, my apologies. It's not a loose term, it's a perfect diagonal term. It's a diagonal matrix of size 2 times 2. Entries on the diagonal, the rest is 0. And here's my verification of, semi-diagonalization relation AP. This time I don't do it numerically, but if you have enough stamina, you can do that. It's the AP product, and this is the PD product. It's more like a general argument here because when you multiply a matrix, any matrix by diagonal from the right-hand side, all you do, you scale in columns by diagonal entries. And the other thing we discussed with you at length on Thursday is that if you multiply any matrix which is given the column structure by a factor from the left-hand side, all you do, you multiply every column by the same A from the left-hand side. And that's the semi-diagonalization relation. You don't have inverse here. You don't have inverse here, so you don't have full diagonalization relation in this case. You don't have inverse for the obvious reason because this is not a square matrix. You don't have enough pairs to make a square matrix. You don't have enough pairs to make it invertible. So that's all there is to it. Again, you see, all of the weight of the computations we've done 2 lectures ago on lecture 18. That's all there is. That's all there is to this particular exam. Any questions? When do we start? How much time do you need? We're good. I just show them one example, and they will be yours. All right. One last example of diagonalization, which is a little bit more advanced. I mean, I'll tell you why I call it a little bit more advanced. Again, all of the needed pre-computation we have done earlier. I'll show you where it is on the website. Any questions in relation to this? Good. So there was example where we discussed with you projection transformation. It's lecture 19 probably again. Yes, it's the one. Eigenvalues and eigenvectors over projection map. If you remember this, 2 lectures ago. We had a matrix. That's the matrix. This is the one we had 2 lectures ago. For this matrix, we discovered 2 eigenvalues. Here they are, 0 and 1. And interestingly enough, look at this. Interestingly enough, for these 2 values, the eigenvalues, we had more than 2. The value, we only had 2 values, 0 and 1. But the eigenvectors, look at this. For lambda 1, the eigenvector was 1, 0, 2 here. One vector associated with the value 1, but with value 0, we had two vectors. Here they go, -2, 0, 1, and 0, 1, 0. Okay? This is a case where this lemma I showed you at the beginning of today's class, the lemma which says that if you have distinct eigenvalues, the associated eigenvectors linearly independent, this lemma here no longer works. Even though vectors we're looking at, they are linearly independent, we need to test this separately by hand. We cannot rely on that lemma because we can't even fit into that setting. In the setting of that lemma, every value has one vector. Well, you can fit this setting into that lemma if you do it like that. If you take, say, you take value 1 with this vector. Let me just go back. So that's a computation data from lecture 19. Let me go down to the dynamic slide now. So it's example 3. Diagonalization example 3. So here's the data from that slide. It's a matrix, projection matrix. Two values, 1 and 0, and the associated vectors, one vector here, and two vectors which come together with 0 value. Okay? So if you try to use the lemma about the linear independence, which says for the distinct eigenvalues, vectors are linearly independent, you can use that lemma here, but it will be of no help actually. Because look at this, you take this value with this vector, I'm fine with this. You take this value with this vector, I'm fine with this. Here's your two pairs and two distinct eigenvalues. The lemma says the vectors are linearly independent. Perfect. But this is not what you need in fact, right? Because when you start building your P matrix, that's your P matrix. If you build a P matrix, which consists of your vectors as columns, you have enough columns, it's a square matrix, you possibly will be able to invert it. But in order to conclude that it is definitely invertible, you need the linear independence of all 3 columns. And you cannot possibly use the lemma for 3 columns, because the third column comes with the same eigenvalue. So you cannot use the lemma for 3 eigenvalues, because you have repetitions between them. But for 2, yes, you can. If you take these 2 pairs, they are linearly independent, but this is no good. I mean, it's a valid claim, but this is no good in terms of convincing everyone that this is an invertible matrix. You can take these 2 pairs if you wish, this pair and this pair. Again, lemma will conclude that this is a linear independent pair, but it's helpless or useless in terms of claiming that this is linearly, so this is invertible matrix. So in this case, lemma is useless, and you need to test that these vectors are linearly independent. You need to test by hand. The only method which we have, the universal one, which works by hand, is the row echelon form. So you need to, well, here it is. So let me just finish first the method. So here's my D matrix, which is built of my eigenvalues. Here it is. Here's my D matrix. I use my eigenvalues on a diagonal, and you see I use my 0 twice. I do so because in P, in the construction of the P matrix, I use the vectors twice, which correspond to 0. And that's why I double the presence of 0 in my D as well. That's right. So that's the components of my semi-diagonalization. I can claim this relation immediately, AP equal PG. If I want to convert this into a full diagonalization, I need to address the issue of invertibility of P. Like I said before, you cannot address this issue from the general considerations. You have to do it here, ad hoc, right on the spot with the row echelon form method. And here it is. So normally when you invert a matrix, it's a quite a tedious thing. By now I hope you know it well. You need to build this augmented matrix where on the left-hand side you put your P matrix, on the right-hand side you put your identity of size 3. It's quite a lengthy writing. Here's all of it. You see my P on the left-hand side, my identity on the right-hand side, and then you do row echelon form. You need to take this to the reduced row echelon form. You need to take it. I have pre-computed this on this slide. You don't have to copy this, in fact. So if I take this to the reduced row echelon form, my slide tells me that that will be this. I hope you'll trust this. Left-hand side, look at this. We have 3 pivots. All columns are leading columns, which means matrix is invertible. So we do have full diagonalization with P inverse, and P inverse right here. This is a P inverse. This is your P inverse. Now you can probably appreciate the advantages of having that lemma, because with that lemma, you don't have to do row echelon form if lemma is applicable. When it is not applicable, you need to do row echelon form, and it's a heavy one, isn't it? I mean, computationally, it's not a nice one. So here's my P inverse. I just copy the P inverse from here, and this is my full diagonalization relation, which you can now write safely with no any problems. What's the time? Any questions?